Hello and welcome back to UML Operator. In the last episode, we kicked off a series on modeling practices with the focus on managing actions so that we can master UML. In the last episode, we kicked off the series with my best practices. And I just want to say that my best practices are incorporated from the practices we're going to talk about in the remaining of the series and industry best practices. We're going to be going over about 20 questions that we need to ask in every delivery exercise, where the 20th one is, are we iterative? Are we working in an agile manner in our modeling delivery exercise? And at the end of this episode, I will apply the best modeling approaches to each one of these questions. I'm going to start with brainstorming, and the focus is on mind map diagrams. The question is, what do we know? What do we need to know? Often when starting a project, we want to expose all of the possible problems, needs, nouns, and verbs to support requirements development. Mind maps are the best way to illustrate the topics to focus on. This is extremely valuable when conducting requirements elicitation, which is one of the 4 legs of requirements engineering. From a central topic, we come up with main topics relevant to that central topic. You may arrive at a conclusion that there are a few separate efforts that are related. Your next question may be, how do actors or users interact with our system or systems? For such interactions or requirements, we use use case diagrams. Developing requirements is the most challenging part of any delivery. The main reason is that most stakeholders think they have all the necessary requirements or collection of problems to solve. While mind maps are great for brainstorming, use cases are best for developing or collecting requirements for any given delivery exercise. In Sparx EA, use cases can expose steps in an experience, flows involved, exceptions, and alternate paths. Each use case can launch scenarios, and scenarios can be used to generate other diagram types, including test cases, necessary to validate requirements, which is an important part of requirements engineering. Now we get to system structure. To answer the question, what is the structure of our system or systems? Here you may collect and start to understand the systems involved in any given problem domain for the project or delivery exercise through use case modeling. But class diagrams provide us a better way to draw out the systems and the structure to later apply use case models. Often, class diagrams are thought of as block diagrams, and more simply put, boxes and lines. Every box can be used to draw out requirements, spark collaboration, and other intelligence gathering exercises. From our block diagrams, we can develop our requirements and then later build those into traceability matrices that allow us to do further analysis on those requirements, taking the nouns and the verbs that we come up with in order to properly solve the question, what is the structure of our systems? In this channel, I have shown you how to build out relationship matrices and relationship views. And this is an extremely powerful way for you to understand the structure of your system or system. Block diagrams also help us understand or experience an actor using our system and platform. Object diagrams can assist in looking at smaller pictures of structure and behavior. Next, we may get to how does data or intelligence move through our system or systems. Data flows, workflows are best suited for activity diagrams. The best way to understand data flows and workflows is through activity diagrams. Activity diagrams illustrate the flows of activities and actions within a system or business process. It models the dynamic behavior of a system by showing the sequence of steps, decision points, concurrent paths, and data flow, making complex workflows and process clear to both technical and non-technical stakeholders. The key characteristics of an activity diagram act as behavioral diagrams similar to flowcharts. They help model complex logic using simple modeling techniques. The next question may be, what happens when things or states change? When you want to understand the state of affairs or state of data collection, good or bad, state machines are a better diagram to choose. In UML modeling, a state is a discrete condition or situation that an object or system can be in during its lifetime, where it satisfies a specific condition, performs an activity, or waits for an event. States are the central components of UML state machine diagrams, visually representing an object's possible modes of operation in response to external and internal stimuli. The next question may be, what are the sequence of events? What is the outcome of the sequence of event or events? When you want to understand the sequence of events between things, these could be systems, services, actors. The better diagram to choose is a sequence diagram. The sequence diagram illustrates how objects or components interact with each other over a specific time, showing the order of messages passed between them or for particular scenarios or use cases. It visually depicts the chronological flow of control and data exchange within a system, with components represented by lifelines arranged horizontally and message flows vertically between them. Our next question may be, how does our design or approach communicate with each other? When you want to expose communication between things, and these could be elements, systems, domains, or actors, the better diagram to use is a communication diagram, which is a type of interaction diagram. It focuses on the structural organization of objects and the flow of messages between them, providing a static view of communication links rather than emphasizing time. Like a sequence diagram, the key features include lifelines representing objects, numbered messages to show sequence, and message flows indicating the direction of communication. The next question may be, what components or modules are impacted or used? We use component diagrams when we want to understand, this is inventory or collect, all the components and modules involved in our system or systems. A special note is that actors, either machine or human, can be considered components of your problem domain or domains. I tend to think that components are software, while hardware, servers or devices, are physical assets exposed in deployment diagrams. Therefore, our next question may be, how and where are our assets deployed? When you want to understand how hardware is deployed or implemented, we tend to use deployment diagrams. The deployment diagram is a structural UML diagram that visualizes the physical architecture of a system by showing how software components or artifacts are deployed onto hardware elements or nodes. It illustrates the execution architecture, including hardware devices, software environments, middleware, and the communication paths between them, providing a static physical view of the system's runtime configuration. Now let's get into some other considerations for answering the remaining questions that we have, such as how do we get all stakeholders, technical and non-technical, to understand the architecture that we're modeling using UML. Regardless of which element or diagram type we use, we need to spend the necessary time when modeling and still move extremely fast, do mind dumps, and return or maintain the necessary level or granularity in our modeling exercises. I tend to think of names as nouns and actions as verbs or functionality. So when I'm reviewing or analyzing a problem statement or statements, for example, requirements, I'm extracting the nouns and verbs and modeling as clearly and descriptively as I can. To answer the question, how do we ensure we are working at the right level, make sure you're maintaining a consistent granularity in your modeling. We are never completely done with a diagram, element, or relationship. Getting to the right level of details in a given model can be difficult. This is why collaboration is extremely important. Even if you're modeling by yourself, you can still use collaboration features such as journaling, discussions, and other socializing capabilities within Sparx. This leads us to the question, are we using or thinking of the correct action types? When you want to understand the behavior by humans or machines in a particular model or diagram type, extract the verbs and model for each using the right action types. While RACI is a framework and not an action type, we can derive actions or tasks when considering the things that are responsible, accountable, consulted, or informed through CRUD considerations. Think about it. Are you watching YouTube or are you creating content for YouTube? Our next question may be, how do we model control or flows such as data flows? Dealing with control and data or information flows, having a separation of concerns, and even where to start and stop can be complicated, especially in complex modeling exercises. First, we need to understand the differences between control flows and data flows. Control flow is about the sequence of execution, while data flow is about the movement of information. A control flow is triggered by the completion of a preceding action. A data flow is triggered when the required data or object tokens are available. To deal with the separation of concerns, we must explicitly model both control and data flow rather than mixing them. Doing this, we can clarify the logic of complex systems during analysis and design. Next, we get to the question, how do we protect or secure and isolate data? In UML modeling, encapsulation refers to the object-oriented principle of bundling data attributes and methods or operations that act on that data into a single unit, such as a class. The next question may be, what conditions and guards need to be in place? In UML modeling, especially in activity diagrams and state machine diagrams, a decision node represents a branching point where a control or object flow splits. And a guard condition is a Boolean expression that controls which path is taken. The two elements work together to model conditional logic. This leads us to the question of how do we determine or ensure what should happen happens first? Maintaining traceability or modeling data relevance both horizontally and vertically is critical to modeling and computer-aided software engineering. In UML modeling, traceability refers to the ability to establish and explore the relationships between model elements across different levels of abstraction or stages of the development process. It allows developers to track how requirements are designed, implemented, and tested, providing a clear understanding of the why and the how each component is delivered. This leads us to the next question of how do we trust that our design or approach is correct? UML modeling tools support both validation, which checks the model against formal rules to ensure correctness and compliance, as well as simulation, which executes the model to observe its behavior and verify its functionality dynamically. Validation often uses object constraint language, or OCL, to define rules, while simulation tools execute models to generate snapshots and traces, providing early feedback on design adequacy and revealing potential issues before implementation. A UML model can be transformed into an executable model, which can then be simulated. Tools can generate prototypical instances or snapshots of the model to visualize its behavior using standard notation like object diagrams. All right, we're going to wrap up now. We stepped through the 20 questions that we posted at the beginning, and I've provided answers here in green for each one of those. Now, the answers aren't absolute. You're going to use modeling diagram types and the actions required, the practices required to implement those that work best for you. The bottom line is that you have a problem to solve. That's why you're modeling. Or you have an idea that you want to design, and you're going to go through all of the scenarios necessary to reach a conclusion. And if you haven't answered all of the questions, well, That could be defect injection. That could be a problem at the end of delivery or throughout delivery. So we covered a lot here. We have more practices to go through. So in our next episode, we're going to talk about baseline practices. It's going to touch a little bit on versioning. We're going to talk about managing relationships, dealing with model relevance. We're going to have another episode on journaling, discussions, and collaboration. I talked about it a great deal in this episode. We're going to get into more than one Sparx project, and it doesn't necessarily mean it's a large project. You just have multiple Sparx instances and how you can connect those, especially around reuse and making your modeling, your delivery of your ideas and your projects more productive. We're going to have an episode on brainstorming. I talked about in this episode about mind mapping, but you can brainstorm off of any element in your modeling environment. We're going to have an episode on practices dealing with Kanban and agile delivery. Kanbans certainly were around way before the Agile Manifesto. So I want to get back into that, especially as it pertains to Sparx Enterprise Architect and managing your metadata and other data. And then we're going to have an episode in the series on dealing with large project models. And it's very closely related to the practices around more than one Sparx, but dealing with large project models, again, I want to get back to the practices dealing with model relevance, asset management, and reuse. All right. So I really look forward to getting into the rest of this series. And until that next episode, happy modeling.